I'm now a newly minted faculty at IISc, just across town. Thank you. So this will be my first talk as assistant professor. I'm very thrilled about that. And I wanted to talk about some research I had done about looking for dark matter underground. And I thought I spend most of the time giving a pedagogical introduction to looking for dark matter underground, because we haven't had many talks about that. And then if there is time, talk a little bit about my research on that. So here's sort of a map of the talk, at least the research part. First, I would like to convince you that there's lots of room to explore on just this parameter space of the cross-section for dark matter hitting standard model states versus the unknown dark matter mass. Okay, and you do this by going to the optically thick limit, and I'll tell you in a moment what I mean by that. And to do this, you're not thinking about any crazy models or anything. You just need to make minimal tweaks to the WIMP paradigm, and then make minimal extensions to search strategies for dark matter direct detection, and you'll be able to cover many orders of magnitude of parameter space. And then I'll move on to talk about how you can enlist even bigger detectors like neutrino detectors to do dark matter direct detection for you underground. Okay, and then I'm not going to have time to talk about this, but then if you see positive signals in these experiments, you should be able to pinpoint the dark matter velocity spectrum and say a lot about the Milky Way halo properties. And maybe we can talk about this in the discussion section. Okay, so as Tarak mentioned, dark matter exists, and this audience needs no convincing for that. We know this from various pieces of astronomical and cosmological evidence. But here's a question for the students in the audience. Okay, is there dark matter in this room right now? What do you think? You said yes. Anybody else saying yes? Okay, if you said yes, are you sure there's a primordial black hole in this room right now? Is there a cue ball in this room right now? Right, so we don't know the answer to that question, because the answer depends on what the number density of dark matter is, and we have no idea what that is, right? What we do know is the mass density, right? So the mass density is constrained or fit by looking at stellar motion in the vicinity of the sun, and this has been done since 1922 by Captain et al. And so on. And we do know that the mass density is around this value, 0.01 solar masses per parsec cubed. Now that's a sensible unit, because the way you fit it is by looking at stellar motion. So that's the coarse grained density that you can be most sure of. Okay, but then as particle physicists, we want to think of this in terms of GeV per centimeter cubed to do experiments. So if you convert the units, you get that to be around 3 GeV per centimeter cubed. Sorry, 0.3 GeV per centimeter cubed, and that's about 2 protons per T. Okay. So depending on what the dark matter candidate is, the dark matter is either in this room or not. So if it's primordial black holes, maybe they're parsecs apart. The dark matter particles are parsecs apart. If dark matter is in the form of WIMPs or something, then the interparticle spacing would come out to be, for this density, the interparticle spacing would be about 10 centimeters. Then it is in this room. Or if dark matter is lighter than about an MeV or so, if I remember correctly, its Compton wavelength is larger than the interparticle spacing. Did I say larger? No, I mean smaller than the interparticle spacing. Sorry, larger. In which case it behaves more like a field or a wave. And in that case, I wouldn't say dark matter is within this room. I would say we are sitting inside dark matter, right? So that picture is completely unknown until we discover dark matter's microscopic properties. Mega, but I might be wrong on that. I think it's 10 keV, not MeV. If it's below 10 keV, then the Compton wavelength. Yeah. Okay. So given this input, people wanted to look for dark matter, the flux of dark matter falling into Earth, assuming it's a particle. Okay, and this program, these days it is called direct detection, and it began in 1985 with this proposal by Mark Goodman and Ed Witten, so he might actually win a Nobel Prize for the wrong reason if he discovered dark matter, with this paper, where they proposed looking for scattering in the coherent nuclear elastic channel of dark matter on some target, and they were in particular thinking about a sodium iodide target. So this is a sample of a sodium iodide. Well, it's a Mysore sandal soap, but you're not going to take me seriously. But it looks exactly like this. So a sodium iodide crystal would scintillate if particles were scattering on it. So that's exactly what they were thinking of. They were thinking of a detector of this size with a sodium iodide crystal. And they worked out the rate at which dark matter was expected to scatter. If it is scattering independent of the nuclear spin, then you expect, given the density and speeds of dark matter, you expect about 7 events per kilogram per day for a canonical WIMP cross-section of about 10 power minus 39 centimeters squared. That's electroweak cross-section, and a dark matter mass of about a TeV, and so on. Okay, so that's the rate at which they expected to see dark matter. But of course, that experiment was done, and then they didn't see the dark matter. And since then, over the last 4 decades, we've been building better and better and more sensitive detectors. And today, here are the experimental constraints on dark matter hitting standard model targets in the space of the cross-section, the scattering cross-section versus the dark matter mass. Okay, this is not the latest plot, but this gives you an idea. So these experiments have got so sensitive that today we can say with a straight face that we have not seen dark matter all the way down to 10 power minus 47 centimeters square. Okay, that's a ridiculously small cross-section, right? If you think about it, way smaller than strong cross-sections and definitely stronger than electroweak cross-sections as well. So with a broad brush, if you're a theorist, you would interpret this as saying probably Z mediation is dead because that's around 10 power minus 39 centimeters squared above this chart. But maybe Higgs mediation is just around the corner, and we still have to look for dark matter here, right? Okay. Now, if you stare at these plots for long enough, there is a question that you will definitely come up with, which is this really the only parameter space that can be constrained here? Okay, is this really the full dynamical range of this plot? What happens if I'm considering cross sections way above this? And what happens if I'm considering dark matter masses, way to the east of this? Can I just extend this plot infinitely? And these constraints still hold, right? The answer is, well, nothing in physics is infinite, so you cannot extend it infinitely. But you can see where the boundaries actually come from. Okay, you can think about where the boundaries come from. And for that, I'm going to zoom out on the plot and show you a bird's eye view, where now the x-axis spans about 20 orders of magnitude in dark matter mass, and the y-axis spans about 40 orders of magnitude in cross-section. This is basically the mass range in which I expect dark matter to be an elementary particle. And that is a cross-section range that is basically being constrained today by terrestrial experiments. Okay? So we can take an educated guess on how these constraints would look like if I extend this plot, okay? And that guess should look something like this, right? Why does it look like that? I don't know if I have, yeah. So, right, so the reason it's tilted is that I do know that the flux of dark matter or the number density goes as the inverse of the unknown mass of dark matter. So in this space, at least, I know that the slope has to be 1, right? The sensitivity curve has to have a slope of 1, at least in the bottom. And then there are actually 4 different effects that give you, that basically suppress your sensitivity to the sensitivity of your experiment in these 4 different directions. And let's review them quickly now. All right? Okay, so this is how the sum of all the constraints in terrestrial experiments actually look like. All right, maybe there's some updates to that, but it doesn't matter for this talk. Right, so there are 4 physics reasons for why there are 4 boundaries on this plot. So let's start with the southern direction, right? So in this direction, as I go to smaller and smaller cross sections, dark matter is more and more ghostly. That is, it's more likely to just pass through the detector without hitting anything, and that limits your sensitivity. And obviously, the way experiments try to overcome that is to make the detectors bigger and bigger and wait for longer and longer, as Tarak just mentioned. Right? Now, as you go in this direction to lighter dark matter masses, and in particular, when the dark matter mass gets to be lighter than the nuclear target mass, then the dark matter doesn't produce recoils in the nucleus higher than your experimental threshold. Right? So basically, dark matter behaves more like a bug hitting a truck than a truck hitting a bug. So it's not really doing much to the nucleus. Right? So the way experiments try to fix that is to improve on the electronics or use lighter materials such as germanium and other amazing materials like Dirac materials and so on, superfluid helium, etc., and try to reduce the energy threshold of the experiment and look for lighter dark. Now, in this direction, this is one of my favorite directions. As you go to higher and higher cross sections, something really funny happens. Because if the cross section is sufficiently high, dark matter is now interacting so strongly with the shielding of the detector and all the overburden, that is all the rock and the atmosphere above the detector, because usually these detectors are set underground. It's interacting so strongly with all this overburden and shielding that by the time it gets to the detector, it's now slowed down and it's so weary, it's so tired that it's now so slow, it effectively doesn't trigger the detector. And so you miss the dark matter. There might be dark matter going through, but it's just too slow. Okay, so that sets a ceiling to all these bounds. And the way, yes. Well, so colliders have a different, so it's a model dependent question, right? So colliders have a different assumption. So one thing is, if you look at the mass range, colliders, the energy range, the energy limitation of colliders is about here. That's one thing. The other thing is it is sort of a model dependent question, whether you can actually make them in colliders or not. So yeah, I'll mention that in a second. So so the way you try to fix this is, well, don't put your detector underground. If the Earth is stopping your dark matter, put it on the surface, or maybe move it even further up and put it in the upper atmosphere. Or if you don't like the upper atmosphere, put it in space. So a combination of balloons, rockets, and satellites and surface detectors set the constraints up here. So XQC is in particular, it's not a dedicated dark matter experiment. It's a rocket experiment that measured cosmic ray fluxes, and then people recast it to set constraints. Okay, so that's what these experiments are about here.
There's also a seawater test.
So that is, I believe what you're talking about is charged dark matter. And then the charged dark matter gets captured in nuclei in seawater, and then you put a bucket and look for these anomalously heavy charged. Right, but if it's just strongly interacting, we just think of billiard ball scattering, and then it doesn't get captured in seawater.
We can do sufficient
Right. Then if it is, okay, so that can happen, but then how will you detect it is the question. Then how will you can put a bucket in the sea and then there's nothing you can really see, even the dark matter particle sitting in there. Only if it has charge, you can actually, it has to leave tracks, it has to deposit energy in some way for you to see. Okay.
It's weighing the seawater.
Oh, just weighing the seawater. Oh, that, I'm not sure of that, because the mass is not so high. The dark matter, if I increase the dark matter mass, then I'm decreasing the flux anyway. Right. But even there, the flux is so low that over the age of the Earth, I'm not very sure that you can actually increase the mass of seawater per volume. Let's think about it offline. Yes. Okay. Now, finally, in this direction, as I go to higher and higher masses, regardless of the cross section, another funny thing happens. Remember that the flux goes as 1 over the unknown dark matter mass, right? Because the flux is proportional to the number density. So at some point, if I think of this again as my detector, at beyond a certain mass, even if I wait for long enough, there is not a single dark matter particle that would go through the detector in the first place. Right? The flux would have been, that's beyond a certain point, the flux is 0, the integrated flux. So there's not even a single dark matter particle going through, let alone scatter, and that sets the limit here. Okay, so that's where the dark matter particles are rarer and rarer, or diluted and diluted, if you want to think about it that way, right? So on this frontier, the last time, well, before I got into an experiment, the last time an underground experiment set a bound in this direction was way back in 1999 by the Dama experiment, before they got into the modulation business. But since then, no experimentalist has been looking for dark matter in this direction, and this frontier is no longer that active. Okay. Okay, so just to visualize that direction a little bit more, I mentioned this before. Most canonical experiments underground look for quote unquote WIMPs, which are in the ballpark of about 100 GeV. And given that the mass density is 0.3 GeV per centimeter cube, the number density comes out such that the interparticle spacing between dark matter is about 7 centimeters. So in that case, the dark matter might be passing through your body right now. WIMPs might be passing through you right now. Okay, but if you look at where the Dama experiment set their limit, about 2 times 10 power 16 GeV, that mass corresponds to an interparticle spacing of more than 4 kilometers. Okay, so you have to wait really long for one of these particles to get into your detector. And that's what they did. Okay, so, well, now that we have mapped out the frontiers, one obvious question to ask is, hey, what about, what if dark matter is sitting here above beyond the Dama limit? What can we do? Can we look for dark matter here, right? And it's not just, a simple question you ask by staring at a plot. That idea has a lot of theoretical appeal as well, because these super heavy stable states appear ubiquitously in the theories of grand unification of forces. And then from a cosmological perspective, it's very interesting that you can make this kind of particle in so many different ways in the early universe. Here's a few that I've listed, like Hawking radiation from primordial black holes, or the WIMPzilla idea of producing the heavy particles gravitationally at the final stages of inflation, and preheating, which I don't understand very much, and even with thermal freeze-out mechanisms. Okay, you can produce dark matter at higher than 10 power 16 G. Okay, so given this state of affairs, we asked a couple of questions. Okay, when Dama did their search, that was using a 10 centimeter times 10 centimeter sodium iodide crystal and waiting for about a year, and that's what set their flux limit and hence the mass limit. But today, our dark matter detectors are even much bigger than this. So can we hunt for this kind of dark matter with today's detectors? All right, so that's one question. The other is, well, why stop there? Can there be even bigger detectors, not just dark matter detectors? If I have a swimming pool, can I use that swimming pool, for example, to look for dark matter this way? Right? Okay. So naively, I would say, yes, of course, today's detectors can search for dark matter at masses higher than the Dama limit, because whereas Dama was about 10 centimeters in linear dimension, today's detectors like Xenon 1 ton that uses liquid xenon, Deep 3600 using liquid argon, and Pico that uses superheated fluid as detector materials, they're all about 100 centimeters in linear dimension. So that's about 2 orders of magnitude higher in the admitted flux, right? So obviously it seems like you can do this experiment. So does that mean that these experiments have already secretly constrained the high mass end of this picture, and then we just didn't know it? They just didn't present it. Did they already do it, and then we just have to redraw the curve? Well, not so fast, because there is yet another effect in dark matter direct detection that must be accounted for to do this. Okay, and that is the use of multi-scatter signatures. Okay, and I'll tell you what it is here. Remember that the cross section is defined like this. The cross section is basically it's related to the optical depth. The number of scatters per transit through a material is given by that scattering cross section times the number density, which is an extrinsic quantity, times the path length, which is also an extrinsic quantity. Okay, the cross section is God given; it's an intrinsic quantity. All right. So just by looking at this cartoon, well, maybe I should back up a second. So the direct detection experiments, the signatures that they are canonically looking for are basically in the low cross-section limit, where they are looking for at most one scatter of the dark matter as it passes through the detector. Okay, But again, just by looking at this cartoon, you see that if I want to constrain high mass dark matter, because the sensitivity goes as 1 inverse power of the mass, I'm very quickly getting into a regime where the cross section is so high that I cannot avoid having multiple scatters through the detector. Okay, given this definition of the cross section. And a multiple scatter signature is a very different beast from a single scatter signature. And this kind of high energy deposition events are actually summarily thrown out in these detectors, have been summarily thrown out in these detectors for the last 20 plus years. Okay, so it's a completely different beast. You need to do a completely different kind of dedicated search to look for this dark matter. And Dama indeed did look for this multiple scatter signature to set their bound. But since then, nobody has been doing this. But then, as you can see again from just this cartoon plot, if experiments were to do this just like that, if they were to catch these signatures without even just using their old data, for example, just like that, they would double the sensitivity of their experiments in the log space of cross-section. For multi-scatter, that turns out to be not that sensitive. Just like, for WIMP dark matter, it's not so sensitive. So you can look for modulation. Yes, actually you can look for modulation. The short answer is yes, you can. But let's first look for the vanilla signature of just the dark matter transiting. Exactly. Right. Exactly. So the funny thing is, even in the very first paper on detection, the Goodman-Witten proposal, actually, even they had mentioned the multi-scatter signature. And they have this funny sentence that says, along a large range of masses for strongly interacting dark matter is probably already ruled out by the simple observation that sodium iodide does not glow in the dark, right? So the fact that there's not much energy deposition going on should already give you a lot of constraints. Okay, so let me try to quickly wrap this up after this. So this multi-scatter signature I performed by joining the Deep 3600 dark matter collaboration. I'm a theorist, but for this search, I joined this experimental collaboration. And we set some of the most stringent constraints on this kind of dark matter. And that's what I'm going to be talking about. But then this is also being done now at the xenon 1-ton and lux experiments with liquid xenon. And my experimentalist collaborator, Ben Broerman, has already done a search for this at PICO, the PICO experiment, and the result will appear imminently in his PhD thesis. Okay. Okay. So the reason I chose to join the deep collaboration as opposed to the more famous, xenon and 1-ton or other collaborations is that what I realized is I say had because now it's slightly different. They had the biggest dark matter detector on. Okay. Today it's xenon n-ton, which is a little bigger than that. But with a linear dimension of 130 centimeters, they had the largest detector, and which meant they had the greatest flux of dark matter being admitted. And that would mean that they would set the best bound on the mass frontier of dark matter. Okay, and I made a back of the envelope calculation for the sensitivity, and I spoke in the collaboration meeting and convinced them that they would be the first detection experiment to reach the Planck mass. Okay, period, just by the back of the envelope flux calculation. So they graciously let me into their collaboration, and after 2 years of weekly meetings and poring over data, we finally did set the first detection, first bounds on the Planck scale mass. Here are my amazing collaborators on the experiment. And the basic idea here is that we did a waveform analysis to look for multiple peaks as the dark matter transited the detector, giving you energy deposition. Okay, that's the basic idea, but then it was obviously more sophisticated than that. We had lots of fiducial cuts to do and so on. Comparing with simulations, we were able to set a bound. So I'll just jump to the punchline. Here it is, again, in the cross-section versus mass space. Now the dynamical range, starts at about 10⁻⁷ GeV in this plot. And we did this for two popular models, if you want to call it that, of dark matter that's being presented in experimental papers. One where the per nuclear cross-section, scales as 4 powers of the atomic mass. This is when you have, some vanilla contact interaction. You get 2 powers of A from coherent scattering and 2 powers from ratios of reduced masses and so on. And the other is to consider some sort of hardball dark matter scattering where you don't differentiate between the perinuclear and perinucleon cross-section. Okay. Nevertheless, the thing that I want you to focus on is that we set a constraint on a wide range of cross-sections, but also we just about kissed the Planck mass. Okay, so that's the limit we set, and really in this business, there's nothing special about the Planck mass. It's like crossing the sound barrier. There's nothing, it's not like the world is going to come to an end or something. It's just that you start to see more interesting and new physics phenomena. That's just what happened here. We hit the Planck mass. What that means is now we are able to set constraints or make statements about some really interesting models of dark matter, which we can talk about later. Good. This flat one, that is a limitation of the simulation. Basically, at that point, all the waveforms are merging so much that you don't distinguish them in the simulation. So that just puts a sharp cutoff for us, yes. Whereas this ceiling, the slanting ceiling, comes from the overburden of the yeah. These are coherent scatterings, yes. So this is coherent scattering, that is not coherent scattering. So A power 4 is coherent scattering. Yeah. No. So the de Broglie wavelength, it's not the content. So the de Broglie wavelength of scattering goes as, well, the de Broglie wavelength goes as
V by M.
1 over the momentum.
Oh, sorry, one more.
And the momentum transfer goes as a reduced mass.
Uh-huh.
Right? And the reduced mass, however heavy I make dark matter, the reduced mass is always a nuclear mass.
Oh.
So you always get coherent scattering.
Okay, so this was something at least I understood it wrong all along. I thought that after a certain mass, it's no longer coherent.
No, I would say after a certain mass, it is always coherent.
Okay.
Yeah.
Thank you.
In this system, it so happens that the reduced, so just to give you numbers, it's 40 MeV. The momentum transfer is 40 MeV. Whereas we know that the nuclei and all are 200 MeV. So if you inverse it, then yeah, you are getting coherent.
Are you sure that these gamma bounds actually cut off there, or they can only fit the analysis?
No. So the gamma bounds do. You mean this vertical thing? Yeah, they do cut off there. It's a sharp cutoff because the flux, they look for the usual 90% person, 2.3 events for 90% confidence limit. That's where the 2.3 limit is. 2.3 events limit is. That's why we also have a sharp cutoff, sharp vertical cutoff. Okay, I don't know how much time I have left. Okay, very good. Okay, so I'll just wrap this up then. The second question, of course, is, we have all these amazing dark matter experiments, but can we repurpose even bigger detectors like neutrino experiments to join this hunt? Yes, of course, the answer is yes, otherwise I won't be talking about it. So what kind of neutrino detectors? Well, the most suitable we found are liquid scintillator neutrino detectors, because the idea is that only in these kinds of detectors, if you collect enough light inside the detector and catch them in the PMTs, you are in business. Okay. Whereas if you are using a water Cherenkov detector like Super K or SNO, the erstwhile SNO and so on, you don't really get a signal because dark matter is actually moving in very slowly, only 1,000th the speed of light. So the scattering is all non-relativistic. So you're never going to produce a Cherenkov radiation in these detectors. Okay. And similarly, the flagship, the Dune experiment in the US is also not going to be suitable because the detection here is a charge readout, and because of that, the energy threshold is just way too high. It's like 10 MeV or something, whereas I can only deposit per scatter only like 40 keV or something. Okay, so really only SNO plus and borax are in business. And here is borexino on the right, and xenon 1 ton on the left, and with physicists for scale. So obviously, borexino is much bigger than xenon 1 ton. In fact, its effective surface area and hence the dark matter flux is at least 100 times greater. And so that obviously means the mass sensitivity is also at least 100 times greater. You can go at least 100 times larger than the Planck mass, for instance. And as for the cross-section sensitivity, you just need to satisfy whatever selection trigger they have in their data acquisition system. Okay, the selection trigger meaning so much energy deposited within so much time and so on. So let me actually skip this slide quickly, and then I'll show you another plot like this. The signal here is, given that for a linear dimension of this size, about 10 meters or so, given that linear dimension, the typical transit time for dark matter is about 10 microseconds. So the signal is basically looking for a continuous deposition of photoelectrons over this 10 microsecond transit time. The other sharp feature here is that because these particles are so heavy and the target, for example, carbon in the liquid scintillator is so light, the dark matter is basically going very, very straight. So it's very collinear, and you can work out the deflection angle to be about 10 power minus 60. And given the amazing timing information that these guys have and the vortex reconstruction capabilities, this collinearity can be exploited to just like that pick out the dark matter signal of a slow moving particle continuously depositing photoelectrons. Okay. So here's some more on the signal. So if you look at 10 microsecond windows in borexino, a typical dark matter signal, boson fluctuated, would look like this. So many hits in a 10 microsecond window. Whereas most of the background actually comes from what is confusingly called dark counts. This is basically thermal agitations in the PMTs in the detector. The rate of that is typically looks like this. So if I have dark matter 10 power minus 28 centimeters squared, then obviously this is a lot more populated than this, and I can definitely set a constraint, right? So that's the idea here. There's also some, once in a while I get energy deposition from carbon-14 decay because you cannot avoid having carbon-14 in liquid scintillators. And then just from the look elsewhere effect, once in 10 years, I'm going to get a highly populated window. Okay. So given all that, you can put all that into the calculation and get the sensitivity. And that sensitivity looks like this, okay? I should have shown the deep constraint here, but no matter. For comparison, here is the xenon 1 ton limit if it were to do this kind of experiment after 1 year. But if SNO were to do it in 10 years, then the limit would be all the way up to here at 10 power 21 GeV, which is like 2 orders of magnitude above the Planck mass. And given their existing trigger, you could set a constraint on the cross section at 10 power minus 26 centimeters squared, but then we also propose some improvements which can improve the sensitivity by a factor of 100. So let me quickly summarize. So, before Goodman and Witten, this was the picture we had of dark matter scattering on nucleons. That's that's the way. Another way to phrase it is this is the answer we had for the question of whether dark matter actually touches this or not. Right? That's a very fundamental property of dark matter. And then we entered this era of looking for dark matter scattering, and their sensitivity was this parameter space, this much parameter space. And today we are in the thick of this program, and with all sorts of amazing sensitive experiments. This is the extent of the searches. And then when I got into the deep 3600 experiment, this much parameter space was carved out using multi-scatter signatures, and in particular, we touched the Planck mass. And if xenon 1 ton were to get into this business, and even more importantly, if SNO plus and other liquid scintillator experiments like Juno and so on get into this, they should be able to set constraints on lots more orders of magnitude in parameters. So, okay, I'll stop there. Happy to take questions.
Thank you, Nirmal, for a very interesting talk. So we can have questions. Yeah.
So of course, this talk is basically about the direct detection, but I was just thinking about the astrophysical consequence of the higher cross section.
Yes.
don't you think that if you arbitrarily increase the cross section with the nucleons of this dark matter, then you will have more dark matter content on the galactic disk?
More dark matter content? No. That's just set by the density, right?
No. So if the interaction is
oh.
large,
Yeah.
then it will capture more dark matter, or because the baryon is in the disk of galaxy.
Right.
And you will have like more probability to interact with the dark matter. So it should, depending upon the what kind of interaction is, it will either deplete the dark matter from the galactic disk, from the usual NFW,
right,
or otherwise it will like capture more dark matter.
Right.
In the
So
galactic disk.
it will, okay, I understand what you're saying. So it will happen, but then the densities are such that, you won't really deplete so much dark matter from the here. The interaction probabilities, the dark matter and the baryons are still sufficiently separated that you won't actually capture so much. But there is another astrophysical effect that can happen, and maybe I have a slide showing that, or maybe not. Okay.
Mhm.
So, above this, I didn't show those constraints here. When the densities were higher in the early universe, the dark matter, if it has strong enough interactions with baryons, that can induce some drag,
Right.
in the Boltzmann equations, basically.
Uh-huh.
And that will show up as weird distortions in the CMB and so on. And that can help you set constraints. And of late, people have also been setting constraints using the matter power spectrum itself. So this is actually more related to what you were saying.
Okay.
Dark matter having strong interactions with baryons will actually basically affect small scale structure.
I see.
Smaller scale structure will be harder to form, and that will set some more constraints. So those kinds of things. Actually, there's one more thing, but okay, we can talk about it later.
Yeah.
Yeah.
We'll talk.
Okay, so there was question here.
Yeah. So for the deep constraint in the right hand side, so there should be a like sharp cut. But why is this weird shape? Like there's this
Good question. Yeah. Let me actually go to the bigger plot. Why is that like this?
yes.
So this notch comes from the fact that you lose some flux from dark. If I increase the cross section, so down. Well, how do I put this? Down here, the flux is coming from all over. It's a 360-degree flux. As I increase the cross section, I'm losing flux from underground. So all the mantle and the core and the crust on the other side is stopping the dark matter, and so I'm losing some flux, and that's why I'm losing some sensitivity. That's why you get this weird notch above a certain cross section. Just like that, I'm losing some dark matter from below me.
But that should be true for xenon 1T and these other also, right?
Where this one, so the xenon 110, they didn't do a multi-scatter search, and if you see, the cross section is not getting that high anyway. The xenon 110s, that was drawn using just single scatter. Actually, even if you have single scatter at high enough cross sections due to boson fluctuations. Sorry. Even if you expect multiple scatters due to boson fluctuations, once in a while you expect single scatters. So they look for those single scatters and set that constraint. So this doesn't come into that picture. Yeah.
Thanks.
Okay, so yeah, okay.
Principle measure the velocity of the dark matter directly, and it should give you 220 kilometers per second.
Yeah.
Or something like that.
Yeah.
Okay.
We can talk about it in more detail, but yes, this is we wrote an entire paper on that exactly. That because you can by event you can actually reconstruct the velocity vector of every dark matter particle, and so you can put together a velocity distribution and have direct measurements of the all sorts of properties.
Thank you.
Hello.
Yeah, this one, the deep plot. Okay. Oh, everything in color is excluded. Yeah. By these various experiments, yes. Yes.
Mohanty mentioned something that why are multi-scatters generally thrown away in the analysis up to now?
I think it's psychology that the experimentalists are looking, they're looking mostly for the WIMPs, which have at most one scatter. And it's such a clean signal that that's the analysis they want to do first. And then, they've not been, that's the thing, most experimentalists don't even know that this paradigm exists, that you can have strongly interacting multi-scatter experiment. So doing an analysis with multi-scatter is a little more messy than a single scatter. So that's the reason. Although the funny thing is, it's the multi-scatter signature that has nearly zero background, actually. If you actually get into it, there's nothing that goes so slow and just produces these hits. There's nothing that does it. There are neutrons and things like that that go very fast and make multi-scatter. So that's what I'm trying to convince them, that actually, guys, this is very easy to do, please.
Have they recorded that data?
Yes. So Xenon 110, for instance, they have it all on tape. Every experiment does have a trigger, and they do throw out data from the hose pipe. But nevertheless, they do have a lot of archival data on tape, and it is using that the Xenon 110 people are doing the analysis. I don't know about the other experiments.
Okay, so there are no more questions, so we can thank Nirmal